In the previous tutorial, we looked at the relationship between being above or below the poverty line and the odds of visiting the doctor in the past 12 months when we conditional on gender. So thus far we've only considered categorical covariates in our regression models. Let's go ahead and use the same model as the previous tutorial, but we're going to add a continuous variable, age, to our regression model. First, let's write down the regression model. To fit this model, we have our outcome yi, which is defined as 1 if the individual visited the doctor and 0 otherwise. And now we have three covariates. We have x1, which is equal to 1 if they're above the poverty line and 0 if they're below. x2 is 1 if it's a female, 0 if male. And then last, we have x3, which now represents age in years. We can write down our logistic regression model as the logit of pi is equal to alpha plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3, where yi follows a Bernoulli distribution with expected value pi. Now we've talked a little bit about the assumptions of logistic regression, but they're a little bit more straightforward when you have categorical covariates. Now we've incorporated this continuous covariate age into our logistic regression model. So to fit this regression model, we have to make the assumption that conditional on gender and poverty level, age varies linearly with the probability of visiting the doctor on the logit scale. Now this is an awkward assumption because it's weird to think about things on the logit scale already, and then you have to conceptualize age varying linearly on the logit scale. We're going to go ahead and make that assumption when we fit these models. In the future, when you learn more about logistic regression modeling, what you can do is you can change the functional form of age, you could add in a quadratic term, you could categorize age, and you could see whether the fit of your model improves when you change the form of age in this model. But for now, we're going to assume that conditional on gender and poverty level, age varies linearly with the outcome on the logit scale. So now that we have our model, let's go ahead and fit this model in Stata. As in the previous tutorials, the first thing we need to do is generate the no poverty indicator. We would say generate no pov equals 1 minus poverty. And we need to generate a covariate called female, which is equal to gender minus 1. Those are going to be the explanatory covariates in our regression model. We go statistics, binary outcomes, logistic regression. Our dependent variable is doctor. Our independent variables are no pov, female, and now we're adding in one additional covariate called age. We see it over here in our variable tab. For now, I'm assuming no effect modification between no pov and age. And this is a reasonable assumption in the model. The fitted logistic regression model is logit of pi hat, where that's our estimated p hats, or predicted probabilities of visiting the doctor, is equal to alpha, which is negative 0.81, plus beta 1, which is 0.99, times x1, plus beta 2, which is 1.33, times x2, plus 0.02 times x3, which is h. Let's compare the model with only gender and poverty to the model with age, gender, and poverty to examine whether it appears that age is a confounder of the doctor-poverty relationship. In the model where we include age, the coefficient for poverty is equal to 0.99. When we remove age, we see that our log odds ratio is now equal to 1.0. So we've gone from 1.0 to 0.98, I believe. So there's very little change in the log odds ratio. So because we don't see a change in the log odds ratio, it looks like there is not evidence of confounding by age. And really, we expect age to be a confounder in this model because age is likely not associated with poverty, even though age probably is associated with whether or not someone visited the doctor. But we could assess all of those things. Let's go back to the model that contains age. And let's estimate an odds ratio and a 95% confidence interval for the odds ratio. Now let's go back to the model that contains age, and we're going to estimate an odds ratio and a 95% confidence interval for whether someone visited the doctor, comparing those above versus those below poverty level, when we condition on both age and gender. To obtain this odds ratio, we can use the lincom command. We can say lincom no pov, comma OR. The estimate of our odds ratio is about 2.7 with a 95% confidence interval from 1.4 to 5.1. To interpret this odds ratio, we can say that conditioning on age and gender, the odds of visiting the doctor are 2.69 times higher with 95% confidence interval 1.4 to 5.1 in those who are above the poverty line compared to those below the poverty line. Remember, we've conditioned on age and gender. Now let's test for an association between poverty and visiting the doctor in the past 12 months, conditioning on age and gender, at the 0.05 level of significance. To perform this test, we just need to test whether beta 1 is equal to 0 versus the alternative that beta 1 is not equal to 0. Find that our estimate of beta 1 is equal to 0.99 with standard error equal to 0.327. This leads to a z-statistic that's equal to 3.0. And we know that under the null hypothesis that z follows a standard normal distribution. Consequently, we end up with a p-value that's equal to 0.003. And we reject the null hypothesis and conclude that there is evidence in the data that being above the poverty line increases the likelihood of visiting the doctor in the past 12 months when we condition on age and gender. To find the predicted probability of visiting the doctor for everyone in our data set, we can again use the predict command. This is the same as we saw in the previous tutorial. We just type in predict p-hat. If I go to my data browser, see that I now have this p-hat covariate that varies for everyone in the population, and it varies by gender, it varies by age, and it should vary by poverty status. So I have these predicted probabilities for everyone in the data set. Suppose instead that I was interested in a specific predicted probability. I want to know the predicted probability of visiting the doctor for, say, a 45-year-old woman who is above the poverty line, and what happens when she's below the poverty line. To find this, I can again use the lincom command. So if I want a predicted probability, I have to say lincom. First of all, I need to include alpha, my constant, plus. Next is poverty status. So I want to know 45-year-old woman above the poverty level. So that would mean no pov is equal to 1. So I'd say no pov times 1 plus female times 1 because it's a woman. So her value of female is equal to 1 plus age times her value of age, which is 45. And hit enter. So what I just found here is I found the logit of PI hat when you have someone who is above the poverty line, who is female, and who is age 45. This is equal to 2.36. So if I want to know the estimate of P hat, I have to take the inverse logit. Of 2.36, because right now I have things on the logit scale. To get back to the probability scale, I have to inverse logit. To do that in Stata, you just type display, and the command for inverse logit is conveniently inv logit. Inv logit. And then I copy paste that coefficient in there and hit enter. So I find that the predicted probability of visiting the doctor for a 45-year-old woman above the poverty level is 91.4%. Let's say instead that she was below the poverty level. Then I just go back to this lincom command that I ran. She's still female, age 45, so I leave those the same. But now, for no POV, her value changes from 1 to 0 because she's now below the poverty level. So I change that 1 to a 0 and I hit enter, and I get this new logit probability. So again, I have to inverse logit this guy to obtain the predicted probability. And I find that my predicted probability of visiting the doctor is 79.8 when this woman is below the federal poverty level. So it drops from 91.4 to 79.8 when I change poverty status.